Hello, today I'm going to introduce the Edmonds-Karp algorithm for maximum flow. First, let's recall the Ferguson algorithm. This algorithm's running time depends on the order of selecting augmenting paths, and the Edmonds-Karp algorithm is developed from the Ferguson algorithm by always choosing the shortest augmenting path. Now, we will analyze the Edmonds-Karp algorithm and give an example. The cost of an innovation is order E. When we use the breadth first search to find the shortest ST path, and we can bound the number of iterations as order E times V, and this will give us a maximum flow in time E square V. Now, let's look at the level graph. A level graph includes only those edges from one level to a level which is higher. For example, this is the dialectic graph, and we can find that there are no edges that go to the same level or lower level. And I would like to explain the graph that I'm going to use. Real edges in the graph are black, and dashed edges if their residual capacity is zero. Green residual edges are the reverse edges. We can find that augmenting along the shortest path only creates paths that are longer paths. If we push flow along this path, then we will have reverse edges along this path. These reverse edges are useless for creating a path of the same length, and because they go back up a level, any path that uses one of the reverse edges must use two more edges than the shortest augmenting path that we just used. Next, the shortest path distance must increase every e iterations. Every time that we use augmenting path, we delete an edge from the level graph, the edge that got saturated, like this edge, which got saturated and was deleted. These edges will not come back into the level graph until the minimum path length is increased. As I said, the reverse edges are useless until we can use a longer path. So, if each augmentation deletes one edge from the level graph, then after e iterations, the level graph will be empty and there are no xt paths in the level graph. For example, here the maximum flow value along this augmenting path is 1. The minimum value is 1. So we push a flow of 1 along this path, and we will have a reverse edge from T to S, and the edge AF got saturated, and we delete this AF edge. Then we will have the first residual graph. Next, we will look at this augmenting path, and the minimum value of is 9. So we push a flow value of 9 along this augmenting path. And we will have the saturated path as A. Then we will delete this path which got saturated. Here, because we push a flow value of 9, we will also get the reverse edges. Similarly, here, the minimum value of the flow along this augmenting path is also 9. So we will push a flow value of 9 along this path, and we will have the reverse edges along this path. And the saturated edge is Ft, which will be deleted. Next, the shortest path is this path, and the minimum flow value is 1. So we push a flow value of 1 along this path, and we will have the reverse edges. And the saturated edge is AF, which is deleted. So we will have the final residual graph. We can see that the graph 4 has no remaining augmenting path. All the edges from S are saturated, and there are no ST paths in this level graph. And G5 is the resulting massing flow, with each edge denoted by flow and capacity on the edges. And finally, there are only V possible shortest paths. So for each path of length, we may have up to E iterations. And this Edmonds-Karp algorithm eliminates the dependence of the running time on the capacities. So this algorithm is polynomial. The running time of OVE squared is found by showing that each augmenting path can be found in time OE. That every time at least one of the E edges becomes saturated, and the distance from the saturated edge to the source along the augmenting path must be longer than last time it was saturated, and the length is equals V. Thank you for watching this video.